Okay, now we're going to look at matrices and systems of linear equations. So matrices, it's definitely part of algebra, but matrices and systems of linear equations is really kind of a very fundamental, or not fundamental, very basic introduction to another branch of mathematics called linear algebra. And if you go on to study any of the sciences or engineering or even just math, or if you're going into actuarial sciences, which is also very math heavy, you'll take a course that's called just linear algebra. You'll take a course in linear algebra. And now it's not just matrices that is what linear algebra is, but it's one component of linear algebra. So let's talk about a matrix. So let's do the definition of a matrix here. So if m and n are positive integers, then an m by n matrix is a rectangular array that looks like the following. Now we put square brackets to indicate a matrix, and then we have a sub 1 1, a sub 1 2, a sub 1 3 dot dot dot, all the way up to a sub 1 n, and then you'd have a 2 1, a 2 2, same idea, up to a 2n, and then we continue this pattern down here, and this would be am1, am2, all the way over to then amn. And these subscripts here are basically, they're called indices, and it's double subscript notation, and it's so that we can figure out what element we're looking at, because each one of these A's is an element. Now in this course we're only going to be dealing with matrices that deal with numbers, which is nice, but you have matrices that aren't necessarily dealing with numbers as well. And the way this works here is you want to think of this as row 1, row 2, row m. And this would be column 1, column 2, and then column n. Now the order of a matrix is simply m by n. Then there are other things here. Aij refers to an element in the matrix. For instance, A subscript 1 3 would be row 1, column 3. Then if m is equal to n, we call the matrix a square matrix, because we have the same number of rows and columns. And then in the case of a square matrix, A11, A22, all the way to AMM is what we call the main diagonal. So this is a lot of just terminology here. But let's look at a quick example of a matrix here. So let's look at negative 4, 7, 10, negative 2, negative 3, negative 8. So what is the order? What is a 2, 3? So the order, now you always do rows first, then columns. So how many rows are there? There's 2 rows, and there's 3 columns. So it's a 2 by 3 matrix. That's the order, 2 by 3. What is A23? Well, that's second row, third column. So this is equal to negative 8. Alright, so that's just kind of an introduction to the definition of a matrix, but we're going to want to use matrices again. In this section, we're going to primarily use them to solve systems of equations. So let's go ahead and look at how we use these to solve equations. And what we're first going to look at is writing a system of equations as an augmented matrix. Now this is pretty straightforward. I'm not going to try and write a definition down on how to do this. I think the easiest thing is just to look at an example and show what the augmented matrix is. So let's look at the system of equations, and then maybe we'll solve this one as well. X plus y plus z equals 2. And then 2x minus y plus 3z equals negative 1. And finally, negative x plus 2y minus z equals 4. Now, at the end of the last video, you can remember that I was talking about the fact that when we're solving these, we're really not looking at the variables per se. I mean, the variables are important because we need to know what precisely x is, y, and z, and so on. But when we're doing all the work, we're just really adding and subtracting the numbers in front. So that's what the matrix is going to be here, is we have our square bracket, and then I'm going to write, let's put all the coefficients down of these variables. So it's 1, 1, 1, and then I have 2, negative 1, 3, and then I have negative 1, 2, negative 1. Now this is sometimes, if I were to close this parenthesis right here, or bracket, this would be called a coefficient matrix, because it's just all of the coefficients of the variables. But we want to write what's called an augmented matrix, and an augmented matrix then is going to include also what's on the other side of the equation. Now, many textbooks do this, and I like doing it as well. They kind of draw a dotted line here. Let me make this a little bit darker. Like they'll draw a dotted line here, and then they will write down the numbers here, 2, negative 1, and 4. Now technically the dotted line there isn't necessary for a matrix, but we do this for augmented matrices. One, to make sure that we understand that this specific matrix is representing a system of equations. Because again, matrices can be used for lots of different things and represent lots of different types of problems. And so by putting that there, this is indicating that we're looking at a system of equations. Now, how do we solve this? Well, it's actually going to be almost identical to what we did in the previous section. And I would say it is identical to what we did in the previous video. We're going to do row operations, and we're going to put this in row echelon form. But now we're going to be a little bit more specific about what we mean by row echelon form, because technically we weren't putting those equations into row echelon form before. So row echelon form is going to have where each row's first non-zero term is a 1. First, why don't I actually put the correct wording in here? First non-zero term is a 1. Then the other thing here is that a subsequent row has its first non-zero term strictly to the right of the previous row's non-zero term. And all that is referring to is that stair step that we had drawn there, that we make sure we have the stair step pattern. So let's go ahead and look at the system of equations here. And well, how do I use matrices? Well, we're going to just use the same row operations that we were talking about in the previous video. Now we could rewrite them up here, but there's not really a point to it. They're the exact same. Except instead of saying equations, we're going to be doing just rows. So I've got 1, 1, 1, 2, 2, negative 1, 3, negative 1, negative 1, 2, negative 1, 4. Alright, so let's do some row operations here. So first off, notice that I've got a 1 in this top left. So I want each row's first non-zero term to be 1. And I do have a 1 there. Great. So I'm not going to have to do anything there. Now, I want to get zeros beneath this 1 here. And so I'm going to still do one row operation at a time. So we'd have negative 2, row 1, plus row 2. Now the first row doesn't change, so I've got 1, 1, 1, 2. And then I'd have negative 2 times 1 plus 2. That's 0. Now we do write the zeros down. Negative 2 times 1 plus negative 1, negative 3. Negative 2 times 1, negative 2 plus 3 is 1. And then negative 2 times negative 2, negative 2 times 2 is negative 4, plus negative 1, minus 5. And then we didn't do anything to the third row. But then we can see, well, to eliminate that in the third row, I actually am just going to do 1 times row 1 plus row 3. And if I do that, if I can scroll up here, what do I have? Well, top row would still be 1, 1, 1, 2. I forgot to put my little dotted lines here. And then the second row would still be 0, negative 3, 1, negative 5. Then the bottom row would be, well, I'm just adding those two rows, so this would be 0, and then I'd have 1 plus 2, which is 3, and then I'd have 1 plus 1, sorry, 1 plus negative 1, which is 0, and then 2 plus 4, which is 6. Now, I'm actually going to, because I've got actually, I'll just leave it like this for now, because I want to then get this second row. I'm going to want a 1 here eventually, but for now, I'm going to just notice that if I add these two rows together, this 3 is going to disappear. And so I'm just going to do row 2 plus row 3, and then I'd have 1, 1, 1, 2, 0, negative 3, 1, negative 5, 0. Well, adding that, I'd get 0 here. Then I have 1 plus 0, which is 1. And then I've got negative 5 plus 6, which is also 1. Now I'm not quite done, because this negative 3 needs to be a 1, so I'm going to do negative 1/3 R2. Now I have 1, 1, 1, 2, 0, negative 3, 1, negative. Let's try that again. I'm just copying the exact matrix down. So row 2 is getting multiplied by negative 1/3, so this would be positive 1, negative 1/3, and this would be positive 5/3. And just let me pause the video. Alright, it got it back now. And then the bottom row, maybe, why is it doing this here? Okay, the bottom row would be 0, 0, 1, 1. And now we've actually put this in echelon form, row echelon form. And what we can do at this point is essentially do back substitution. And what I mean by doing back substitution, well, as I said, we've really already done this before. And I'm going to pause again. Okay, so let's start over here again. Might look a little bit different. The program crashed on me here and I had to reload it in, and I lost some of this. So, but we're here now in echelon form, row echelon form, because again, if we look at this, I've got my stair step of 1s going down here, and each row starts with a 1. Okay, so what's the big deal here? Well, now we go back and we write the system of equations that I have. So I have x plus y plus z equals 2, and then y minus 1/3 z equals 5/3, and then we have z equals 1. Now I just do back substitution. I've got z equals 1, so I'd have y minus 1/3 times 1 is equal to 5/3. So this actually gets me y is equal to 6/3, which is just 2. And then I have x plus 2 plus 1 is equal to 2. So x is just equal to negative 1. So our solution is x equals negative 1 to positive 1. Now I'm going to end the video here. We're going to still have another video on this with a couple more examples, but we're also going to start talking about one additional thing here, which is what's called Gauss-Jordan elimination.